Thank you. Okay, so we're on the air. Before we start, I owe you guys an apology. I was rushing with the problem last time. We know that we had to fix one direction of one axis, but then I found out that actually I wasn't really consistent with the sign of the angles that I gave you, the direction of the rotations, and the way I was making the axes move with respect to each other. I was trying to get to the end of the problem, and I didn't anyways. So I'm sorry for that. What I'll do, I have the option to re-record the lecture, but rather than doing that, I'm going to record an additional 5-10 minutes after we're done with this. You don't have to be here, and just go over setting up the coordinate systems again, because there was nothing substantially wrong. I was just ignoring the direction of the angles that I actually put down at the first time. So then you can finish the problem yourself. The procedure is the same. Nothing really changes. It's a couple of axes that are actually oriented differently once you go in the plane of the disk. So I'll send you an email when that video is up. So we can move on with other angles today, unless there's any questions. Has anyone realized that there was something wrong with the angles last time? I encourage you to go back and redo the problems yourself. Because the thing is, every time I solve them, I do them differently. And even the way I name the bases, the way I pick the bases themselves, it's always different. So even if you've seen a problem solved by me in class, you can go erase everything, redo it yourself, and see what you get. Yes?
Even after changing the value of phi dot into uz to the minus phi dot uz because it was opposite.
I can't really remember. I don't want to. Yeah.
Was there anything wrong other than that?
There was an angle that was, I think, let me just sketch it here real quick. Again, go back and watch the video and record again. So this was just to simplify things. I think at the beginning I gave you an angle that was this way, but then what I actually did was the angle going this way in my actual projections. And then the other problem was here, that I believe, at least this is what I have now, that the phi angle was like this, and then when I went and in this plane did the drawing, it wasn't consistent.
So that we corrected with a minus.
You can assume that the angle is the other way, and I think it would work. But again, redo it yourself from scratch. I want to record those additional minutes just to clear out any confusion. Since these are videos that are there for you, I want to have a video that says, hey, there was an error in lecture 8. Relatively small error maybe, but just go and watch it. So no one gets confused, hopefully. Okay, any other questions, comments? Other angles. Okay, so what we've done so far is, in kinematics, of course, that's all we're doing. We parameterize motion of a single particle. That's what we've done so far, actually points. We haven't even talked about masses. And by parameterizing, I mean that your final results, velocities and accelerations, look like expressions where you see x dots, x, y, z, their derivatives, or some other types of coordinates, r, phi, theta, angles and distances. So those are your parameters, right? You pick your coordinate system, you pick your parameters, and your result is going to be a function of those. And the same we've done with angular velocities. At the most, we've seen angular velocities that are the addition of two rotations with two angles, right, in the problems that we have solved. And if you think about it, your final results are functions of those angles, of the parameters that you pick. So now, to generalize rotations of a frame with respect to another frame, again, there is no rotation unless there are at least two frames involved. I guess the first question is, how many parameters do you think you need? We are in 3D Euclidean space, so it's probably pretty easy to get this answer. How many parameters are sufficient to tell me how this is oriented in space? 6 oriented. I don't care about center of mass for now. So that it's only rotating, changing orientation. Its center, it's fixed, and I shouldn't even talk about center of mass. But there is a point that is always fixed with respect to my reference frame, the table, so all it's doing is rotating. So how many do I need? 3 in this case, right? 3 should be sufficient. And other angles are basically one of the several ways to parameterize the orientation of a frame, a reference frame with respect to another reference frame. And again, when I say frame, I say rigid body. So for now, we're not introducing masses, but it can be a physical object. It can be something like this, as long as it's rigid. And so That is one way. Euler angles are used pretty often because they're angles, you can visualize them. We'll derive entirely, and I have to follow the notes here because I need to be consistent with these. We'll derive the expression that gives us the angular velocity as a function of 3 Euler angles. And we'll see that there are some limitations though, but we'll stick with those. We're not doing spacecraft attitude dynamics here, otherwise we'll do quaternions. That's a different story, but we'll stick with them. So we are looking in the end at something that if R is my one of the 2 reference frames, I can call this the rigid body that I'm looking at. Again, for me, there is really no difference between a reference frame or a rigid body. And then let's call A is the reference frame from which we observe the rotation of R. So there are 2 reference frames involved. One is my table, one is this object that is rotating. One thing that is important to understand with this, our goal is finding the angular velocity of R as seen by an observer in A as a function of 3 parameters. For now, I will call them theta 1, theta 2, theta 3, even though I will give them different names. I will just use 3 different Greek letters, but let's say that those are my 3 Euler angles parameters. I want to find this expression. Of course, these are the derivatives, right? Well, it's not only the derivatives, as we'll see. It's the parameters and their derivatives. But anyways, the point I want to make is that we'll find this, but the angular velocity itself, even though it's called velocity, it is not the derivative of any vector. There is no vector you can define whose rate of change in any reference frame is going to be equal to omega. So in other words, you cannot find some b vector dB dt whose dB dt in A, for example, is equal to omega R A. This is impossible, does not exist. Which is strange because we call it a velocity, so when we think about velocity, we think about rate of change or something else, but that is not valid for the angular velocity. It is valid for a point in space, not for angular velocity. So another way to say that is that if I express the angular velocity of R in A in a basis fixed in the rigid body, for example, let's call that E1, E2, E3, omega 3, E3. There is nothing you can define. There are no parameters you can define, basically no coordinates you can define, such that their derivatives are going to give you the 3 components of the angular velocity when you choose a coordinate system to express it. This does not work. And another problem with rotations is that they don't commute. So if I grab this object, and Euler angles are basically defined as we'll see, as single axis rotations about the body axis, about the coordinate system that is fixed with the body. So if this is my body, say that this is your x-axis, or E1, E2, E3, right? And say that I rotate 45 degrees first about E1. And then see y and z, E3 and E2 have moved with the body. So I do, I don't know, another rotation about the third axis, E3. And this is where I end up being. Now if I switch the order and I do this, and then that's my new E, I get to a different orientation. And it doesn't matter if you do it with body axis or you do it with respect to the axes that are fixed to A, you get different rotations. You can't commute them. You can't invert the order. If you do a rotation first about an axis and then about a second axis, it is not the same as doing the second rotation first and then the first afterwards. They don't commute. Okay? That's important to understand. So we should expect something a little more complicated than just what we get with linear velocities, right? Velocities of a particle. So Let me erase everything and start with a few assumptions here. Now, as I said, we'll build these as a function of 3 body axis, single axis rotations. If you have 3 axes, there are actually 12 different combinations you can pick in terms of the order of the rotations. You can tell me that the orientation of this object in space, which is a generic orientation, is that you reach this configuration by doing first rotation about the first axis, then the second, and then the third, or other 11 possible combinations. So my goal is telling you this orientation corresponds to 45 degrees, 35 degrees, 10 degrees, if you follow the sequence 1, 2, 3. With 1, 2, 3 meaning I first rotate about the x-axis, the E1, then about the second axis, and then about the third axis. And they are all body axes. But that's not the only way. You can get to the final attitude, orientation of this object with another combination of rotations. First about the third, then about the first, then about the second. There are 12 possible combinations that you can define.
12 or 9?
12. 12. And, but the most common one that you will see always is called a 3-2-1 sequence. That is really what people use all the time, where what we do is we do it first, we grab the object. So let me first define a few things here. What we have is the reference frame of the reference frame A. Did I call it A? And what did I call the unit vectors? I really don't want to change any names here. Okay, yeah. So they say that this is your reference frame A. E1, E2, E3 is a coordinate system fixed in A. And then you have your rigid body, whatever that is. So this is fixed in A. And this is R. And I want to represent the orientation of R with respect to A. And then possibly write its angular velocity. And we say that we start from what is called a reference orientation. Meaning that I start with the body, coordinate system completely aligned with the big E1, big E2, big E3 coordinate system. So these are overlapped at the beginning. I start from there, and then I want to represent how basically little E1, little E2, and little E3 changes as a function of 3 parameters. So with the 3-2-1 sequence, what we do is we do a first rotation about the body's third axis. We'll see it. We're projecting the 3 different planes. Then we do a second rotation about R's intermediate, or it's a better way to call this, resulting second axis. So this is why it's called 3-2-1. First rotation is on axis 3. Second rotation is about axis 2, which is different from what it was before. Start thinking about this. You start rotating about the third axis. E1 and E2 will draw this, will go somewhere else. And so the second rotation will occur about the little E2 new axis, whatever that is. And then the third rotation is about R's, again, resulting first axis. So wherever this little E1 ends up being, that's your last rotation. And so there are 12 of these possible combinations. You can do a 3-2-1, you can do a 3-1-2, you can do symmetric ones, 3-1-3, You can do whatever you want with those three numbers. You can play with all the possible permutations and represent the orientation of R with respect to A as a combination of basically with three angles. Of course, if I go from a 3-2-1 representation to a 3-1-2, and the final orientation that I'm representing is the same, the values of the angles would be different. And the reason why I stress on this is because Euler angles, as we'll see at the end, have some limitations, and in some cases, you may be forced, we're never going to see cases like that, but it's good for your knowledge. If you're sticking with Euler angles and nothing else to represent the orientation of a rigid body, there are some cases where they fail, and you may need to switch from one type of representation to another type of representation. They are so-called singularities. We will see what they mean. But they're not, this representation with Euler angles is not completely perfect. Every sequence has a point where it fails to represent orientation correctly. That's why people use quaternions and redundant parameters that have no geometrical and physical meaning, because angles, you can visualize them, you can see them. Quaternions and other things that you can use, they don't have any physical representation. You can't visualize them, but they mathematically get rid of the problem that we have with Euler angles, which are great. We use them all the time. We use it for spacecraft, we use it for airplanes. But you need to be careful. You need to know at which point your chosen sequence breaks down, and you may need to switch to another type of sequence. And then you keep going. OK, so let's do this. As I said, I have my notes here that I really want to follow, because otherwise it will become messy. Do we need that? I don't think we need any of this. Maybe I'll leave that rigid body there for a second. OK, so if the first rotation is about E3, what I see in the plane E1, E2, and let's call that angle psi. So this is rotation of an angle psi about E3, which is the same as little e3 at the beginning. So I bring these two, they are the same, into, well, little e1 ends up in what I'm calling here in my notes P1. Just because I need to define reference frames, I really want to use completely different letters here. Makes it easier at some point. So P1 and P2. That's where I move my initial vectors. OK. And this is E3, same as little e3, and P3, of course. That's the first rotation. Second, we said is it's a 3-2-1, so it's about which axis? It's one of these here. P2, right? So if I look from P2 down, I see I'm looking at the plane P3, P1, right? So I have P3 and P1 up here. And I'm calling this angle theta, so theta, which is about P2. So this means that P2 is coming out of the board like this. OK, so I rotate these two, and I get, calling these Qs now, Q3 and Q1. Theta and theta. And this is going to be Q2 as well, of course. And I knew it wasn't going to fit in here. OK. I guess that should be understandable. I can put it here. Last one is about which axis? 3-2-1. So Q1, and so I'm looking at down from Q1 and I see the plane Q2, Q3, right? Q2, Q3. This angle is called phi. I don't need to write that again. Okay. Phi. Phi is here. I'm rotating about, we said Q1. Now, what are these axes that I'm obtaining? Yeah, the final. So which ones? Remember, I'm moving the body. So I'm grabbing the body and I make it rotate. Again, this was my E1, E2, E3. So I do the first rotation about E3 axis. Then whatever is that my new E2 axis, which is here, I do rotation there. And then my last one is the one here. But if I'm making that object rotate, my final goal is telling how the little e's are now displaced with respect to the big e's. So these are actually E2, E3, and E1, right? That's what I want to get. So my defining a certain sequence is just a way for me to go from the reference frame from which I'm looking at that object to the from that coordinate system attached to that frame to the coordinate system attached to that object. I just decide to follow the path 3, 2, 1. But you can do it with other types of sequences, 3, 1, 3, 1, 2, 1, whatever that is. You can get there. It's just different values of the angles. Do we agree? OK. So with those there, which I shouldn't really touch for a while, we are going to write the following expressions to relate all those different coordinate systems. So if I start from that one, I can write that extremely small. P1 is equal to, let me express P1 and P2 in terms of big E1, big E2. Well, it's cosine psi E1 plus sine of psi E2, right? P2 is minus sine of psi E1 plus cosine of psi E2, and then P3 is E3.
Can you please explain why it is E1 and E3 in the last one?
This is big E3, right? Sorry?
Why is it E3, E2, and E1 in the last one? Because after the rotation, E1 and the original reference frame won't be the same as.
That's right. What is the concern? Why these are little E1s, E2, E3, and E3? Because I decide that that's where I want to go.
But even after the rotation, even if any angle is there, we won't be getting E1, E2, E3 the same as the original reference frame.
No, you're not. So the original one is corresponding to big E1, big E2, big E3. That's where I start from. I am imagining, so I know that this object is in some weird orientation, generic orientation in space. I want to represent this with 3 angles. And so I imagine that this actually started from, because that's actually what you do. When, think about this in terms of a point in space. When you say that the position of a point in space is x, y, z, you're measuring it from 0, which is your origin. Now, this is an entire reference frame now. So my 0 orientation is the body axis of this, the coordinate system attached to this body, which is a reference frame 2, are aligned with the A coordinate system, right? So that's my 0 orientation, neutral orientation. They are oriented the same way. And so I want to represent where this is actually, how this is actually oriented by, in this case, using 3 angles and imagining that this object got there by this sequence, even though it didn't probably. Maybe it did something else, but that's one way to represent it. It's just me choosing to use that representation using that sequence. It's a choice. It's like you choose to use x, y, z or r phi theta to cylindrical coordinates versus Cartesian coordinates or something else. I choose to do it that way. Does it make sense? So I do want, as final goal, to get to my little e1's small vectors. I imagine that I get there by doing this. These maneuvers, single axis maneuvers, if you want. Is this clear? Make sense? Okay, so then I do the same. Second plane, yes, Q1. I have Q1, which is minus sine of theta P3 plus cosine of theta P1. Yep. We have Q2, which is P2, and then Q3, which is going to be cosine of theta P3 plus sine of theta P2. And the last one is, I'm hoping to write everything in the same column here. Little e1 is Q1. Little e2 is cosine of phi Q2 plus sine of phi Q3, right? And then little e3 is minus sine of phi Q2, that's right. Sine of phi Q2 plus cosine of phi Q3. Okay, nothing special here. So I have basically taken the body and I've reoriented it to its final orientation. Does this make sense? Okay, I want to do one more thing now. Let me give these. So here we have 4 coordinate systems, like the little e1s, the p's, the q's, and the big e's. So let me call those something. I'm calling E. So this is just a placeholder. Basically, this basis. It doesn't really want to be a vector, but it's just a placeholder for me, just to make it shorter. P is P1, P2, P3. Q and then, well, this is actually A, right? So let me actually, as I said, that these are placeholders. I don't want to actually put any equals here. I just want to say that this was actually my body, right? This is R. So reference frame where this is fixed is R. And I imagine that there is a reference frame where called P, just with the letter P, where these 3 vectors are a basis and they're fixed. Then a reference frame Q where these are fixed. And then A was my original big E1, big E2, big E3. Yeah. OK. Yes? Which one? Q3. This one. Cosine of theta P3 plus sine of theta P1. Thank you. Yep. Did I have it right? Did I have it wrong? I had it right. OK. Everything else look good? So why am I going through all this pain? Well, the goal of kinematics is again, we wrote it at the beginning when I said in kinematics we care about velocities and accelerations of points, velocity, angular acceleration of reference frames. So in the end, I'm going to use these 3 angles to write an expression for the angular velocity of r with respect to a. That's what I want to do. I want to parameter. We've done it in problems. We've done it with 2 angles only. We haven't realized that we were using some kind of Euler angles, but that's what we've done so far. So what is the angular velocity of r in A? I really don't feel like I want to erase anything here. How would you write this? Actually, this is the right spot to put it down. Remember, I said that this is built as a sequence of single axis rotations. So for each of these rotations, which involve 2 frames each time, 2 reference frames each time, I can write a simple expression for the angular velocity, right? So this, how do you break it down? Before I actually write any formulas, any time derivatives of angles.
Omega AQ, QP, and QR.
So I go from R to Q, then I go from Q to P, right? And then I go from P to A. Does that make sense? Addition of angular velocities. You can add as many as you want. Because that's exactly what we've done. We went from R to P, because R was starting as in the neutral reference orientation. It was oriented as the coordinate system in A. So I go from R to Q. Yeah, I'm sorry. I'm going this other way. Yeah. R to Q. Then I go from Q to P. And then I go from P to A, because I'm going from the body to A, not the other way. Okay? Does it make sense? It's the angular velocity of R, the reference frame R, with respect to as seen by an observer in A. So if I want to use this expression of the addition of the angular velocities, remember the little trick of going with the superscripts from right to left. So I'm going from R to A, and I want to add all the intermediate single rotations. So I go from R, which is little e1, little e2, little e3 to Q, and then etc. So what are those? What are these things? One by one. What is the angular velocity of R with respect to Q, as seen by an observer in Q? An observer in Q is someone who is glued to this Q1, Q2, Q3 coordinate system and is using it to measure how this other coordinate system, E1, E2, E3, is moving. And the only thing it's doing is a rotation about the E1 axis.
Phi dot Q.
Phi dot.
Q1 for E1.
Yeah, let's see how we want to write it here. It doesn't matter. Little e1, yeah, one of the two. They're the same thing, right? So that is that term. Then I have QP. How is Q moving with respect to P? Something very similar, right? Theta dot P2, Q2. What am I using here? I'm using Q2. It doesn't matter. I will have to transform them anyways. And then last one, PA. P is psi dot. So this is this term here. Psi dot P3, for example. Yeah. Okay. See, I already have an answer. Almost. I already have the angular velocity of a generic reference frame R, which could be a physical rigid body, an actual body, an actual object, with respect to A as a function of the derivatives of those three angles. And as I told you, in principle, this is fine. But what it is actually done, in this case, even though we're still in kinematics, and I told you it's fine to mix bases that belong to different coordinate systems, well, in this case, we really want to write everything in one consistent basis. Why? Because physically speaking, the angular velocity is actually, for example, on board the spacecraft, it's measured by devices called gyros that give you this vector expressed in a basis which is fixed to the spacecraft. So in this case, it will be little e1, little e2, little e3. So it's a good idea to actually put this in that reference frame, in that coordinate system. See, I make mistakes I shouldn't make. So if you want to use that, we need to transform the vector. Okay, so E1 is fine. Little e1 is fine. I don't like Q2 and P3. And so how do we, I think this can go now. How do we get them? Okay, let's start with Q2. Where do you get Q2 from? Probably down there, right? How about, I mean, you can do the Kramer rule with the, you can find two of those at the same time, but one way could be, I can take these and multiply it by the cosine of phi, take these and multiply it by the sine of phi, subtract both of them, and I should get a Q2. So if I do cosine of phi little u2, that is going to be equal to cosine squared of phi q2 plus, this is the q, cosine sine q3, right? And then if I said the second one, I do the sine of phi. I can do this, right? I can do whatever I want. Multiplying both sides of an equation by the same quantity, I can do that. Minus sine squared of phi q2, I hope, otherwise this is not going to work, plus, good, I get the same thing because I want that to go away. And so I do this equation minus this equation, which is going to give me that q2, because cosine squared plus sine squared is 1, is actually equal to cosine of phi little e1 minus sine of phi e3. That's one way of doing it. And I like that much better than trying to remember the Kramer rule because I don't like it. Doesn't matter how you get it. You just have to find Q2. Oh, that's Q2. And then what do I need? P3 there. How do you do P3? It's either this set of equations or this set of equations. Which one? Second one? Maybe? So I already forgot which one I want. Which one do I want? I want P3. Okay. So I can do the same trick between the first and the last, I think, but then I will need Q3, right? That's okay. If I do the same thing with first and last, what do I get? Let's try to be quick here.
P3 is equal to Q1 cos phi, Q1 sin theta.
You know, instead of being quick and making mistakes like last time, I'm going to do it all over again. I don't want to make the same mistakes. Okay, so I'm going to multiply this by the cosine, right? Because I want to eliminate Q3. Is that right? P3, I want to solve for P3. So I do cosine of which one now? Theta Q3 is going to be cosine squared of theta P3 plus sine cosine P1. How much time do we have? Okay, we have time. And then I see that probably should do the same with the sine here with the first one. Q1, right? Is this a good plan? You want to do it another way? No? You don't care?
We can form a matrix equation.
Yeah, that's exactly what I don't want to do because I'm lazy. Okay, minus, plus. No, you can, absolutely, yeah. So I'm trying to see what's going on. Q1, Q3, so I will actually have to find Q1 and Q3. Oh, well. So with this, I get the P3 is equal to sine theta Q3. Oh, well. Okay. Q1 is little e1, though. No. Sorry. Never mind. Okay, that's fine. What do we do now?
Q1 is E1, Q3 is E2 sin phi plus E3 cos phi.
Q1 is E1. right? Using that one. So this goes away. Good. Q3?
E2 sine phi plus E3 cos phi.
You're using which one?
Second and third. Third one.
Second?
And third one, second and third. Multiply with sine phi and the second with the cos phi and third one.
Okay. So what I get here is Q1 and Q3. Yeah, Q3. So this sine of phi E3 twice sine of phi E2. Make sense? I never said this was going to be painless, but that's the way it is. Okay, so I need to substitute everything in here, and the final expression you get is the following. Now I don't need this anymore. This is what I have. Omega RA is going to be equal to, if I collect everything together, phi dot minus psi dot sine of theta, little e1. Then I have, for little e2, I'm just jumping to the final expression here. Since we already have the vectors expressed as we want them to be expressed, cosine of phi, little e2, because I really want to make a few comments here. Cosine theta, cosine phi minus theta dot sine phi. You can check if this is right or not. It's right. It should be right. You can do it with another sequence. The procedure is the same.
So how do we actually check which sequence is correct? Like which sequence is the most efficient?
Oh, they're all the same. I mean, you end up with formulas that are exactly that they look like this. There's not much difference. You will have sines and cosines anyways. So efficient, it depends what you mean by efficiency. Computationally speaking, if you need to implement these and actually integrate numerically, they're all equivalent. The points that I wanted to make is one, now if you look at that expression, remember when I said before, is everything okay? This is what I'm getting now, right? Little e3. This is what I have. I have expressed those components, little omega 1, omega 2, and 3, these scalars. I have found them to be these ugly expressions here. Now you can see right now that there's good luck trying to find one vector whose derivatives give you that stuff. Yes?
So when you're solving for Q2, could you go and say Q2 is equal to P2?
Yeah.
And then say P2 is equal to negative sine, yada, yada, yada.
Where do I need that though? Why do I need Q2? I don't see Q2 here, or P2. I mean, this is the one that we solved and it's fine, and I've used it. For the second one, I don't really see Q2.
We're going back to when you're trying to solve for Q2.
Oh, here, this one.
Yeah. So before you get to that.
Yeah. So you wanted to solve Q2 starting from here. Q2 is equal to P2. Okay, and then where do I go?
Go to the top and say P2 is equal to that, and then isn't.
But then I don't want to use the big e's. I want to express everything in the small e's, right? That's what I wanted to do.
I thought that big E's and small E's were the same thing.
Well, they are the same thing. They are the same thing in the reference orientation. I imagine that's my zero. There is no rotation between the two frames, but they're not. I just think that I imagine that I got to my final orientation by doing this sequence that starts from that condition. Remember, that's your zero. It's like starting from the origin when you want to go to a point. That's your zero. Yes? You can that expression we can write it in another basis. You can go with big E, but practically speaking, if you are on any moving, I mean this is dynamics, so we're probably looking at moving vehicles of some kind. Even even a piece of machinery, they are usually equipped with sensors that give you those. They are attached to the body. So if this is a spacecraft moving around, the gyroscope, whatever it's mounted inside, it's attached to the body and it's going to measure those three in the body reference frame. So that is practically used on airplanes, spacecraft. That's why it is expressed that way. But you're more than welcome to play with these and express omega RA with the biggies or with the P's or any of these. It's fine. You can mess around with them as much as you want and find a final expression. What I told you more than a couple of times is that in kinematics, in principle, we don't care about expressing everything in the same coordinate system, but in this case I do, because this is what it's practically done. Sensors do measure these three quantities, whatever they are. And this is also a nice thing to look at to understand that there is no vector you can define that will give you this as derivative. There's no way. One comment I really want to make before we wrap up about these Euler angles is you can now go back to your problems that you solved before with only two angles and try to see how this simplifies, because one of these rotations is not there. You should probably recognize the angular velocities that you computed for a couple of problems that had two angles involved. You will recognize some of those terms, and some will be zero, because one of the rotations is zero. It's not existent. Yes?
So let's say there's a point in a reference frame, but with a different coordination, and that the second reference frame could be reached by only two transformations.
Right.
Only two rotations.
Right.
But we won't know how, but we might be choosing some other rotation which requires three. So how would we know which will require two, which we need to make for two, and which we make for
That's a good question. Yes, you can. So the problems I gave you, actually, I marked the rotation. So I was already giving you that two were fine. But you could, in principle, in the problems I gave you, go from the initial orientation to the final one with three rotations. But I think what happens is that you always get that one of them is zero. I mean, if this is all it's happening, why bother trying to find a sequence that gives you more than one angle that is not zero?
That we can say because we have a reference frame fixed.
Yeah.
And horizontal to the plane.
Yeah.
What if we don't? Like we have.
Well, this is the case where you don't. This is the most general case.
So three is always.
Three is always the most that you can get. If you have an orientation, if you have an orientation where you can represent it with only two, so let's put it that way. If you pick a sequence, 3, 2, 1, it is possible that the orientation of your body is given by two angles that are non-zero and one is zero. If you change sequence, it may be very well that the three of them are non-zero. Okay? So in the problems I gave you, I picked the angles for you, theta and phi, for example, right? Before. But if you pick any other angles about weird axes that you completely make up at 45 degrees with respect to the shaft, you can do that. Then you will get three angles that are probably non-zero, all of them. It will make your life a nightmare, probably. But yes, absolutely. If you change sequence, the angles change. So you can have a sequence where one angle is zero, and then you switch sequence and it's not zero. I really need to make this point. Can I go 1 minute over? I hope so. So this is big E1, big E2, big E3, and I'm looking at this sequence, and this is valid for any Euler angle type of rotation. So if I rotate about the first axis of an angle psi, this is where I get my, I don't know what I called them. What did I call them? This was Q, right? Q1, and this is Q2. Okay, now if I rotate about Q2 exactly 90 degrees, guess what happens? This Q1 vector is going, which is still in the plane E1, E2, is going to be oriented exactly like minus big E3, right? It's going to point down. And that is going to be your, I think the last ones were the P ones, right? Your P1 vector. So now you're supposed to do your last rotation about this one of some other angle, which we called, what do we call it, that? Phi. But do you see the problem here? If something like this happens, this is called the singularity, because You can pick infinite combinations of these angles. Say that this is 10 degrees, and this is another 10 degrees, and the sum of them gives you a 0. And you can pick 20 degrees and 20 degrees, and these give you still 0. And it's the same orientation. And you can go on with infinite combinations of these two angles whose difference is the same, and you're still representing the same orientation. And that is substantially, absolutely wrong. If you want to choose parameters that represent your state, position in space for a particle, orientation of reference frame, they need to be unique. There needs to be a one-way correspondence. You can't tell me that the position of this point is x, y, z, you give me numbers, but it could also be some other x, y, z's. It's not unique anymore. You can throw it away. That type of parameterization doesn't work. So Euler Angles, these asymmetric sequences, so 3, 2, 1, 1, 2, 3, when you don't see the same numbers, they all have the same issue at 90 degrees. The symmetric ones, I believe, is a 0 rotation that gives you, on the second axis, the same problem. We can talk more about this, but the bottom line is, when you use Euler Angles, you know which sequence you picked. When you approach 90 degrees in this case, you need to be careful. You either switch type of representation. So you basically, it's like solving a problem in Cartesian coordinates, and at some point, one of the coordinates gets close to a certain number that you don't like, well, you switch to polar coordinates. That's exactly what is done in practice, unless you want to use something else. But this is a limitation that you need to be aware of, because Euler Angles are not perfect. They have an issue. But we still use them. An airplane will probably never go 90 degrees like this down, right? So you don't want that. So it's probably fine. You're going to be away from singularity, because if you get there, you probably have other issues. So that's Euler Angles in a nutshell, more or less. As I said, I'll be in the next room.